In section 2.2.3, we'll learn one more aspect of sinusoids that's important, called frequency, and we'll explore its use in various applications. Here's the definition. The frequency f of a sinusoid with period p is given by f equals 1 over p. So notice that the frequency and the period have a reciprocal relationship. While the period gives the length of the interval for one fundamental cycle to occur, when we invert that, the frequency will count how many cycles per one unit. If the x-axis is measuring time, for example, we would measure the frequency in cycles per one unit of time, cycles per second, cycles per minute, or something like that. This can be used to model the pitch of a sound, the color of light, or the magnitude of angular velocity, for example. Consider example 5. The volume of air, V, in cubic centimeters in the lungs of a certain distance runner is modeled by the equation V equals 400 sine of 60 pi t plus 900, where t is time in minutes. Consider for a minute why a sine wave is a useful model for the volume of air in the lungs. As a person breathes, the volume expands to a maximum, and as a person exhales, the lungs contract to a minimum. Then the cycle happens all over again. The lungs expand, and then they condense. The periodic nature of the sine wave is the perfect model of something like that. Notice for this model that the independent variable is t, so we would plot time in minutes on the horizontal axis. The dependent variable there is V, volume in the lungs, and this is measuring cubic centimeters of air. To answer question A, we need to consider the graph of this particular sine wave. What are the maximum and minimum volumes of air in the runner's lungs? Well, first of all, notice that this sine wave has been shifted up the vertical axis by 900 units. So its center line is going to be at V equals 900 cubic centimeters of air. The amplitude is 400, so we know the sine wave is going to reach 400 units above this line and 400 units below this line. So 900 plus 400 is 1300, and 900 minus 400 is 500. So the sine wave would follow its basic nature in between those lines. So the maximum volume then would be 1300 cubic centimeters of air, and the minimum volume would be 500 cubic centimeters of air. So notice the range of this function is from 500 to 1300, from the minimum amount to the maximum amount. Now here's a good question. How many breaths does the runner take per minute? Now if we consider our basic sketch here for the graph, we can easily determine the length on the t-axis that it takes for one fundamental cycle to occur, and that's going to be described by the period. So we'll take our original period of the sine wave, 2 pi, divide by that coefficient, which we normally call b, and we can see after reducing that the period is 1/30 of a minute. That means in a length on the horizontal axis of 1/30, one complete fundamental cycle occurs. And let me be specific, this is the period. So in 1/30 of a minute, one fundamental cycle occurs. Now think about what that means. That means that the runner takes a breath and exhales and then starts the process all over again. So if we invert this to get the frequency, that is, the frequency is the reciprocal of period, then we can conclude that the runner takes 30 breaths per minute. Now, to clarify what one fundamental cycle represents for this particular model, that is one breath, an inhale and an exhale. So again, inverting that period would give us 30 breaths per minute. Sine waves and cosine waves, because of their periodic nature, are extremely useful for real-life models. The runner example was one such example, but they're also useful in astronomical models. Let's consider example 6. The graph below shows the positions in June of Ganymede, Callisto, Io, and Europa, the 4 bright satellites of Jupiter. Jupiter itself is the center horizontal bar. The paths of the satellites are nearly sine waves because the orbits of the satellites are nearly circular. Think about translating the unit circle into the sine wave on a rectangular coordinate graph. That's essentially what we're doing here. We're taking the circular path of the moon and stretching it out in a rectangular coordinate system to generate a sine wave. The distances from Jupiter to Io, Europa, Ganymede, and Callisto are 262,000, 417,000, 666,000, and 1,170,000 miles, respectively. Use the graph to complete the table. So for each moon, we want to calculate the period and frequency. Let's begin with Io. Notice that on the graph, Io is the green curve. I want to measure how long it takes in days for Io to complete one fundamental cycle. So I'm going to recognize the beginning of a sine wave and the end of a sine wave. So I can see one complete fundamental cycle here. Now I'm going to approximate the period. This is easier if you have a ruler. So the rough estimate here, we could say a period of 2 days. So one complete cycle in 2 days. If I invert that, it's going to give me the frequency. That is, Io takes about 1/2 of its cycle per day. Let's consider the moon Europa. Europa is given by the blue curve there. So we just need to find the beginning and end of one complete fundamental cycle of a sine wave. So I'm going to use this little segment right here. Now this is a very rough estimate. We're just making an approximation from the graph. So here we could estimate the beginning to be about 8.5 days, the end to be 12 days. So that's about 3.5 days. So one cycle in 3.5 days. So if the period is one cycle for every 3.5 days, the frequency is going to be the reciprocal. So we'll approximate here about 0.3, so almost 1/3 of its cycle completed per day. Now think about it. How do these values compare to the moon circulating around the Earth or rotating around the Earth? It takes approximately 28 days for the moon to go around the Earth. So these moons are covering a large distance in a short amount of time. Ganymede is the moon here in orange. So again, I'm recognizing the beginning and the end of a fundamental cycle. This one appears to be about 7 days. So if we invert that, I'm just going to approximate it, 1/7, about 0.1 cycle per day. Let's measure the last moon. Callisto is graphed here in yellow. Now notice I didn't start with the portion that goes up on the sine wave. I started with the portion that went down, but that's okay. You can measure it from one point to its corresponding finishing point. So from about 13.5 to 30 days gives us about 16.5 days. Still a shorter cycle than Earth's moon, but a little bit longer than the others. When I invert this value and round to the nearest tenth, I'm going to get about 0.1 cycles per day. The last two measurements there are very similar, simply because I rounded to the nearest tenth. So period and frequency have a reciprocal relationship. They're describing the same aspect in different perspectives. The period describes the interval required for one complete fundamental cycle to occur, whereas the frequency describes how many cycles or a portion of that cycle occur in one unit. If we're talking about time units, that can be per second, per minute, or per day, as it was on this example. Let's consider one more application, and this is a sneak peek of a model that you'll see frequently in differential equations. Example 7 says a weight hanging on a vertical spring is set in motion with a downward velocity of 6 centimeters per second from its equilibrium position. So imagine having some sort of rigid support, and you attach a spring to that support, and on the end of that spring you hang a mass. Now, the original spring has an equilibrium position, but when you hang the mass on that spring, it's going to stretch the spring until it comes to a new equilibrium position or a new resting point. So we can imagine the equilibrium position to be the x-axis. Now, if I reach up and I pull that spring down, because if you saw something like this, that would be irresistible, right? If you pull it down and release it, then that mass is going to oscillate up and down, above and below its equilibrium. In the absence of some sort of damping force, it's going to oscillate indefinitely. If we model the position of that mass above and below its equilibrium, we're going to find that it follows a sinusoid as it oscillates above and below, and we map this against time. Again, we can model that with a periodic function like a sine wave. Now, one thing that can be a little bit challenging about these models is that because when I pull the spring down, let me say why here. When I pull the spring down, it elongates the spring. We say the displacement is positive. Whenever that spring oscillates back up and compresses the spring, we say that its displacement is negative. So motion above the x-axis indicates an elongated spring, and motion below the x-axis represents a compressed spring. So the signs can be a little bit confusing there. A formula that gives the location of the weight in centimeters as a function of the time t in seconds is x equals 3 sine of 2t. Oops, I was right the first time. Position is x. Okay, so notice here that our dependent variable is x and our independent variable is time. So we're measuring the position of this mass above and below the equilibrium as x relative to time measured in seconds. Find the amplitude and period of the function. So because this function has a coefficient of 3, the amplitude is 3 centimeters. And because we have a coefficient on the argument, the period is going to be the original period 2 pi divided by coefficient 2 to get pi. So in pi seconds, that is about 3.14 seconds, this mass will oscillate through one fundamental cycle. Let's construct the graph of this sine wave with a period of pi and amplitude of 3 on the diagram. So we're talking about a sine wave which begins and ends its fundamental cycle on the t-axis. Halfway in between the beginning and the end, it has another x-intercept. Now let's go ahead and label our scale here. I'm going to use 1 tick mark per unit. And we know the amplitude of this particular sine wave is 3. So halfway between its first 2 intercepts, it's going to have its maximum. Halfway between the last 2 intercepts, it's going to have its minimum. So the mass is going to oscillate according to this sine wave. So there's one fundamental cycle of the sine wave. Remember, when the mass is, or when the function is above the x-axis, that indicates that the spring has been elongated or the mass is below equilibrium position. Whenever the curve is below the t-axis, the horizontal axis, that indicates that the spring has been compressed or the mass is above equilibrium position. Let's see if we can answer the final question. How many oscillations does the weight undergo per second? Now remember, the period describes one fundamental cycle in pi seconds. The frequency is the reciprocal of that. 1 divided by pi, or let's go ahead and approximate that with our calculator. 1 divided by second pi, and we'll round it to the nearest tenth, is 0.3. So approximately 0.3, and this would be measured in cycles per second. So in 1 second, now remember, pi is about 3.14, so about a third of the way there, we have 1 second on our t-axis. Our weight has undergone about a third of its complete cycle. So remember that period and frequency have a reciprocal relationship, and they can be used to model all kinds of important applications.